Welcome to my YouTube channel, STEM Cafe, where we make everything easy, fun. We study science, technology, engineering, and mathematics. I make everything easy, fun, easy to recall, easy to understand, comprehensive, and comprehensible at the same time. We make it so simple and fun for easy recall and to tackle any form of question that comes under any topic treated in this channel. My name is Oladimeji, and I'm happy to be treating this topic friction with you today. Please, if you have not subscribed, kindly subscribe and share. Let others know about it. It's good, and your comments is very appreciated because these are the things that keep us moving. You can also send your questions and whatever assistance you might need. Let us know. Whatever way I can handle it, I will. Now today our topic is friction. And friction is a force. It arises when we have two bodies in contact. Two bodies in contact. When these two bodies are in contact, and this one tries to move to this side, a resistance arises. And the resistance is always opposing the direction of motion. So if this motion is here, resistance will be opposite. And this resistance that occurs to motion, when it occurs that between two bodies in contact, it prevents sliding of motion, prevents sliding of the bodies. We call this force frictional force or friction. We call it friction. A force that resists or opposes motion, relative motion between two bodies in contact. So, in this instance, today, we'll be dealing with what we call solid friction. That is friction of solid bodies. And mainly I will talk about dry friction. Because so many things affect friction. Lubricant on the surface, dust on the surface, oxides on the surface. It affects frictional force. But in this instance, we are talking about analysis of bodies where all these do not exist. And we call it dry friction or Coulomb friction. Let's see. Some people have made research about how friction occurs, and they have been able to give us some laws. One of them is F.P. Bowden. He looked into it with sophisticated equipment and realized that when we have a block like this, and it is on a surface. No? So it's on a surface like this. Please look at it. And it's on a surface like this. That the contact is made between this place and this body. This force causes something like pressure and allows some points like this to tack. You know what we talk in welding? This pressure causes something like tacking. Small dots. Like some points that will be like it is welded, but not really welded. So when we apply force here, it will have to break this something like bond. We have to break it. And this is what causes that friction. So, and as it is still going, it's still there, but not as much as when it is stagnant. He also now made us to realize that if this body is now turned sideways like this, if this body is turned sideways, you understand that the number of points that we tap together, that is, those points will be the same as when it is on the other side. Why? Because the pressure, the force down, the normal force is the same thing. So This is what makes it to behave like it does not. It is the frictional force is not proportional to the area of surface in contact because the force is the same and it determines the number of points that will be tacked together. So, one, we realize that the frictional force is not determined by area in contact, by area of contact, but normal force or reaction. You can see. So it's the force that matters. Now let's talk about how does this friction occur, or the characteristics of frictional force. Characteristics of friction. You know, we have said that the frictional force, it opposes the relative motion of two bodies. Now let's have a body like this. And we have a force F parallel to the surface here now. This force, let's say it starts from 0. Let's say 0 force. The body will still be in stationary. This, you know, we are talking about something like tacking, like welding at different points. This force must continue to increase. Do you understand? And as this force is increasing, the frictional force also increases. It will continue to increase until it gets to a point that it breaks all this tacking, all these points, all this something like adhesion, adhesion, gumming, until it breaks it. So this force, let us say this force is increasing straight like this, until it gets to a point that it is equal to the forces that joins these surfaces together. Then it starts motion. That one is what we call static friction. That one is what we call static friction. And the highest value is referred to as limiting value. Limiting value, you know, let's call this one force. And we refer to this as FR because FR is equal to F. So we have limiting value. After it has broken that, you know, mountain, that peak, after it has gotten to that peak, any little force, again, it starts moving. It will start moving. But what we realize is that as it moves, the frictional force reduces. And we have this one. This one is for the static. And this one is for the kinetic. Kinetic. So it breaks this one for static. It breaks that one for the static. And then it continues with this frictional force. So most times, in our analysis, when the body is not that really moving, we talk about this static. But when it is moving, sometimes we take it to be equal for ease in calculation. But sometimes they will tell you it is not the same thing. So please take notes. Now, we have talked about this. We are now going to talk about something we call coefficients. Why? Because this frictional force, we have said that it is proportional to the force, the normal reaction to the surface. But it is still dependent on the nature of the surfaces. Like the frictional force between glass and wood is different from the frictional force between iron and wood. So it varies from one type of material to another type of material. And that is why we talk about coefficients of friction. We always represent it by mu. And it will be equal to this force, you understand, that starts the motion or continues the motion with constant velocity. If it is constant velocity, yes, that is for kinetic coefficients. But generally, it is equal to this force over normal reaction. This one I say normal reaction as in perpendicular to the surface. It is very, we call it normal reaction. I like to write N. I don't want to put any suffix. N. So this one that I wrote out, we always refer to it as N. And this N does vary too. The force applied, depending on how it is applied, affects N. The slope of the body of the surface affects N. So these are things we look at so that we will demystify anything that looks like mystery in handling of frictional force. And most times you will see question. Look at the resistance as negligible. We are trying to say that ignore frictional force. Though you can't really see that kind of situation in nature. But for ease in analysis, we always put that. Especially when we have assumed that the surfaces are very smooth. Like we talk about this smooth surface and that. But without friction, I wouldn't have been able to write on the board. I wouldn't have been able to walk like this. The motion of the car on the road wouldn't have been possible. Application of brakes wouldn't have been possible. All the brakes themselves wouldn't have been effective. The tires on the road, everything works on friction. Either for car or lorry or bicycle. So even in grinding our pepper, those who use grinding machines and all that stuff, grinding stones and so many other things. So those are the necessities. But where we have problem with friction is, and we try to reduce it, is when we use it in machineries. It adds to the load. It reduces the efficiencies of our machines. Now, let's look at how the force affects normal reaction. Because that is what we use to calculate our coefficient of friction most times. And that is what we use in analyzing our questions. Now, we are talking about coefficient of friction. And I've been able to let you know that the static, for when it is at rest, the frictional force will increase from 0 until the force applied equals to this limiting value. And then as it moves, it reduces. We now want to look at how the applied force affects the normal reaction. Because we use the normal reaction, look at it. We use the normal reaction to calculate coefficient of friction. That is what friction really depends on. This frictional force over N. So F, frictional force. When you want to calculate F, really, you always try to work out the normal reaction. And it is this. The unit for this one is nothing because it is ratio. So we don't have unit for the name, just like ratios of angles and for the trigonometric ratios. Now, if you have a body like this, and you want to calculate the N, normal reaction, it has a weight, W. The normal reaction for this one, when we have a force here, please note, if this force is not as big as mu N, friction also exists, but motion does not arise. Because this one will be resisted by another force here when there is no motion. So there will still be Fr whenever there is F, even if it is not as big enough as mu N, as coefficient of friction times the normal reaction. Please take note of that. Let's call this force P. As you see, the normal reaction in this instance, this one goes like this, this one goes like this. It does not affect anything. It doesn't give component to this one because it is perpendicular to this. Are you getting me, please? It is perpendicular to this. So in this instance, N equals to W. Please take note of that. Very important. This must be gotten. Now, let's look at another situation. When we see P like this, and it sustains theta, you can see, in this instance, our N is different. Our N changes. So we need to resolve this along parallel to the surface and perpendicular to the surface. That will make us to be able to calculate our N. You can see that the component that is useful for the motion of the body will be P cos theta. Please take note. This component here, P sin theta, now affects this one. How? N In this instance, please, n plus p sine theta is equal to w. That is the weight of the block or the body. So in this instance, our n will be equal to w minus p sine theta. Can you take note, please? Very important. And if you want to know, if they tell you that, oh, motion starts, tendency of motion has occurred, it means that this one here is equal to the mu r. That is, if motion occurs. That is, now, it means that mu n is equal to p cos theta if tendency of motion arises. Please, that is, motion is about to take place. But not always like that every time. I'm just trying to illustrate something. So you have gotten, in this instance, n equals to w minus p sine theta. Straight off, the vertical component is equal to the upward component is equal to the downward component. Simple. And this might be up to mu n. It can be more than mu n, and it can be less than mu n. The components that remains, in case this one is more than mu n, the remaining components will be used to accelerate the body. So, if p cos theta is greater than mu n, that is, p cos theta minus mu n is equal to n a, where m is mass of the body and a is the acceleration. Please take note. Take note of that. Another situation might arise. This is another situation. We have P pressing down and moving the body. In this instance, you can see that we have P sin theta coming down, P sin theta coming down, and P cos theta goes forward like this. You can see. So in this instance, our n will be equal to w plus p sin theta. You can see. So the direction at which this force is applied affects the value of n. And then the horizontal component might have some other help, might exist alone, and do other stuff. It can cause motion, it can cause tendency of motion, that is at equilibrium, and it can do anything. So the horizontal component is equal to p cos theta, and this can really help a lot in doing so many things. So when you are doing things like this, the best thing is to, resolve the forces into components that will make it easy for you to do your calculation. And sometimes you might need to hide the forces once and for all. When you get there, you cross the bridge. And look at these forces, the components, as entity, as bodies, separate bodies. Like this one, look at it as separate from this. Though you have resolved one single force, look at them as different individuals, even as human beings, and you will see it as fun, catching fun. Like this one is doing this one is doing his own. Look at them separately, and then you enjoy it. Now let's look at another situation. Now look at this. And we have P parallel to this surface. We have said that the reaction should be normal for us to be able to work with coefficient of friction. So this one will be like this, perpendicular to this one, and this is n. Now, how do we calculate n from this? You can see from our resolution that we have done in the past, n is equal to w cos theta. Very straightforward. It's like this. You see? And this one, everything here is equal to 90 degrees. You have treated this before. So this place is 90 minus theta. So this place is theta. And this is w. This place is theta. So this component is w cos theta. And this one down, you can see, we have this one already down. We have w sin theta. Down already. So, depending on the direction of motion, this has already added to the resistance we are we are thinking of experiencing. It has added to the frictional force that we are treating. If it is going up, you can see that the component is down. But if the body is moving down, it does not reduce the friction and it does not increase the friction. But it is helping the force that is acting to move the body in either way. If the body is going up, the force here, this one will affect it. You can see this one is going up, this one is going down. So it is adding to the frictional force. It is not that it has also become a frictional force. It is a different force due to the slope. So frictional force will now come in from this place. And so frictional force will now be mu n. So frictional force will become mu n. So in this instance, you can see what we are experiencing. Sometimes you don't even need to apply P. The body will not move yet, depending on the extent at which you move, the slope is, and the coefficient of friction. So please note how to calculate your friction in this place, in this instance. When you get to the examples, you will see. Now, let's look at another situation. When P is again like this. Can you see? Another thing entirely. This one, from the weights, you have already gotten W sine this down. This P. So let's look at it like we are resolving the forces along the parallel of the face of the of the slope. So look at this. This is P sine alpha, P cos alpha. So you can see our n now. Our n in this instance will be equal to W cos theta minus P sine alpha, or n plus P sine alpha is equal to W cos theta. That is it. So just look at it like you are breaking it along the parallel of the surface on which the body is sliding. That is it. So from here you can calculate your mu n and other stuff. So we have along the surface, we have P cos alpha. We also have W sine theta. They act against each other. In this instance, sometimes you might need force from up here to move down. You can also need it. So the most important thing is for you to be able to resolve the forces along in any direction that will help you to solve the problem. You can also have P from here. It can be like this and move up. Let me show you. Now, so let's say I have P like this now. You can see. And I'm moving this body up and I have this alpha here. So which means I have the components that is doing the useful work will be P cos alpha. And P sine alpha is acting down, adding to this weight. So you can see. So I have P sine alpha. So in this instance, N will be equal to W cos theta plus P sine alpha. And other stuff you can easily resolve. Now let's see how we do investigation about friction. Now we have a body on a flat, straight surface, and we have something like a small play here. So on this, we will be applying weights. This one will take as frictionless pulley. So this weight here, this F here will be equal to F here. You understand? And so W here will be equal to the normal reaction. So when we have it like this, N will continue to add weights, like I told you before. But even if the weight here is small, there is a frictional force opposing this and is equal to this. The only thing is that it's not big enough yet to break the adhesion on the surface is here. So for us to get our coefficient of friction, mu, when we realize that this body starts moving or shows tendency of movement, that's for static, we will make it to be equal to F over N. But when it is moving already, you can, because if you leave this force as it is here, it will cause acceleration. It will cause acceleration. Because most times, static, the limiting friction, is more than necessary for kinetic friction. So once you remove it and you realize that it is now equal to that, it's now giving you constant velocity. That is kinetic, coefficient of kinetic friction. Let's move that on mu k. So all these things that I've been discussing is studied under an aspect of science. We call it tribology. This is the science for study of friction. For study of friction. And I'm telling you, we will really go to a bit high place on this because it's fun. Now, we have talked about the work of Bowden, and they came out with some things they refer to as laws of friction. They told us that from study, 1, friction opposes motion. So most times, when you are doing your work, friction will always be in the opposite direction. 2, friction is independent of area of contact. You can see. Now 3, friction is proportional to normal reaction. I told you the perpendicular components of the force acting on the surface. I also want us to look, I have talked about that one on the horizontal surface. Now let's look at how we can look at the body. I want us to look at further into the one on inclined plane. Now before I go into body on inclined plane, let's look at something. We have this body here now, and we have a normal reaction. We have a force like this, going like this. We have a frictional force like this, you know, and we have W like this. When it's at the point of movement, F will be equal to FR. So we look at it independently like this, and we say, okay, total reaction on the surface now will be this. Total reaction on the surface will be this. And the angle between the total reaction and N, theta, will be equal to arctan FR over N. And you know what FR over N is? That is mu. So it is arctan mu. That is the coefficient of the friction. Now, what I'm going to do now will make more sense. We have a body like this. Before I go on, yeah. Now, so please note, depending on the direction at which this force acts, that is what will determine the direction of the friction. If the motion takes place in this place, either you have attached some other forces along, the direction of the motion determines where friction acts. If the motion is in this place, motion place, is not dependent on F, it depends on motion. The direction of friction is dependent on direction of motion. Direction of motion. And it is always opposite. Opposite the direction of motion. So please take note. The force can go here. So many forces can go in either direction, but the direction where the motion goes determine where the motion takes place, determine where friction acts, and friction acts always opposite to the direction of the motion. Now I can now talk conveniently about when the body is on inclined plane. Inclined plane. Like I told you, the motion can take place in either direction. Can take place in either direction. Now look at this. Let's call this one theta. We have theta here. We have n like this. We have w like this. You can see. So if the motion takes place upward, frictional force comes this way, and the reaction on the surface is in this direction due to the friction. If the motion takes place here, the frictional force goes in either direction. Now, which means that the analysis is always good to be relative to n on the surface. Now let's look at something. This place, we have w cos theta. We have w sin theta. If motion is not taking place at all, depending on the coefficient of friction between the surfaces, the reaction on this place will be this, and it will be w this total force, total reaction, let's call this one R, will be n, the sum of n and this one. You understand? The sum of n and this one. And you know, frictional force is trying to take place towards this place. So it will continue like that. It will continue like that until motion is about to take place. Now, if we move it and we realize that motion is about to take place here, you can see that this space is w cos theta, this space is w sin theta. So when motion is about to take place, F will be equal to w sin theta, and N is equal to w cos theta. So mu is equal to F over N, which is w sin theta over w cos theta, and this will be equal to tan theta. Can you see? Can you see the almost something? Although, but look at the analysis now. So with this one too, you can use this one to find the coefficient of friction between the two surfaces. If it is something you can increase the slope, and the point at which sliding is about to occur, that gives you the coefficient of friction, the tangent of the angle. So you can see. Now, from this, when you are analyzing, you can conveniently reduce the number of forces you are going to work with. This one goes like this. So automatically, this one will be like this. R. You see? R. You can see. And R will be the sum of this and the sum of this. And the theta between the two of them, when motion is about to take place, will be equal to R tan mu. So it makes our work very easy in some higher analysis. So if you can do this, later on when we get there, you see, it helps a lot. So like, instead of looking at this, I will just say, okay, this is mu, and then from this one, I can easily get every other component conveniently. But just take note, between the normal reaction and the total of the forces, the angle is theta, which is R tan mu. That is what I want you to take note here. So when we have it like this, and this is, you know, I told you that if we can increase it and this body starts sliding, the R tan of this is equal to mu. So this angle here, we call it the angle of repose. We call it angle of repose. That's the important thing to learn here. I talk about the laws of friction. Now let's summarize what we have discussed in this. Now let's look at some basic facts that determines the magnitude of friction. Now, one, if no motion takes place, the magnitude of the friction force can have any value between 0 and mu n, depending on the applied forces, but will always be such that the body is in equilibrium. That is when no motion is taking place, no acceleration. There is a limiting, that is maximum value, to the magnitude of the friction force that can be generated, and the value is mu n. We have stated that. Limiting value of the friction is only attained if relative motion is about to take place between the two surfaces in contact. When motion takes place and we add another force, it causes acceleration. But if motion has not started, we have not gotten, if the motion is not about to start, we have not gotten to the limiting value of the friction. When relative motion takes place, the friction force on the body is opposite direction to that of the relative motion of the body. I stated that also. I told you that friction is not about the force, but about the motion. In which direction is the motion taking place? Friction goes the other way. The coefficient of friction depends on the nature of material and nature of the surfaces in contact. So which means that if the surface is rough, the coefficient of friction will be greater than if the surface is smooth for the same type of material. But for different types of material, like between glass and iron, between glass and glass, between wood and wood, coefficient of friction differs. The friction force is independent of the area of contact, but on normal reaction. If motion occurs, the kinetic friction is less than the limiting static friction force. All these things we have stated, and now we have summarized. With all these tools in our possession, we can handle friction, calculation of friction, at least to a certain extent. Let's start. Now let's look at conditions that arise due to a body being on inclined plane. You know, when we have a body on horizontal plane like this, we have the weight and then normal. Everything, the normal will be equal to the weight. Then, if no force acts on it, frictional force will be equal to 0. Well, if a force acts on it, P, Fr will be equal to P. And if we increase P, at a point, the body will try to show tendency of motion. So, we have gotten to the limiting frictional force. Therefore, P will be equal to mu n at that point. P will be equal to mu n at that point. If we increase P further, which is, this one is equal to the frictional force. That is the maximum frictional force. That is the maximum frictional force. If we now later increase P, there will be motion, but the frictional force will not go beyond that value. Any extra force generated will cause acceleration of motion, because acceleration of the body due to the extra force. So A will now be equal to P minus Fr over n. And we have already noted that this one is equal to mu n. So which is P minus mu n over n. That is for on horizontal plane. So now let us now see the body inclined at angle theta to the horizontal. For flat surface, that is horizontal for surface, at that one theta is equal to 0. But in this instance, we are talking about a situation where theta has value. Now, when we have it like this, this is the force that is generated on the surface. We have n that is equal to mg cos theta. We have a force directed downward, which is mg sin theta. Automatically, frictional force will be upward. That is the frictional force. So, until motion begins, frictional force will be equal to mg sin theta. Now let us now look at the relationship between mg sin theta and Fr. N is equal to mg cos theta. We have another force downward, that is mg sin theta downward. So Fr, therefore Fr over n will be equal to ng sine theta over ng cos theta, which is equal to tan theta. So the body will remain stationary until the relationship between Fr over n, when Fr over n equals to mu, which equals to tan theta, there will be impending motion down the plane. You can see. So any little force afterwards, the body starts moving down because the frictional force is acting upwards. You can see. So at this point, it's in equilibrium, so it can move down easily. Now, the only situation that can arise here is what will be the force necessary to move it up. When theta equals to phi, force to pull object up. And what will now happen then? When we now try to push the object up, it doesn't need any force to hold it stationary at this point, because it's just at equilibrium. It's just having tendency to move. So if we want to move this body up now, this Fr will now act downward. So you can see Fr will now act downward. So if you want to move this body up now, P will now have to overcome ng sine theta and Fr. You can see. So P will be equal to ng sine theta plus Fr. But at this point, tan theta is equal to mu. So we have is equal to 2 ng sine theta 2 Fr. So to even move the body up at all, you are going to need this. That is when theta is equal to phi. So which will be equal to 2 ng 2 ng sine phi, please. Thank you. Now, if the angle is more than phi, if theta is more than phi, that's the condition we want to look at now. So if theta is greater than phi, the body will move down on its own. So the body will start moving down on its own because the force generated down is more than the frictional force that the surface can generate. Let's look at what will happen. So here, ng sine theta, and this place is n mu n, which is n tan phi. Therefore, and you can see that this place is also equal to n tan theta. Therefore, n tan theta is greater than n tan phi. So the condition that can arise here is you might need a force to balance it so that it doesn't go down, to stop motion down. To stop motion down, you just need little force to add to this one to stop motion down. So you have this. So ng sine theta will be equal to P plus ng cos theta mu, and this one will be n tan theta minus n tan phi. So just break it down. That's what the answer will be. Now if I want to move the objects up, you know that ng sine theta is far more than f in this situation. So I have to contend with friction downward again because it has to act against motion. So this one is mu n, and everything must be equal to this force going up. So P, to move body up, P will now be equal to n tan theta plus n tan phi. You know, in all the situations, n is equal to ng cos theta. This one is varying, but this one is constant. So we have solved that one. Now, if theta is less than phi, normally there will still be ng sine theta down. And frictional force will act upward. But this frictional force will not be up to the limiting frictional force. The frictional that is supposed to be overcome for motion to start. So there won't be any motion in this situation. There won't be any motion in this situation. It will still be stationary. There will be stability. Then the condition that can arise in this situation is you will need force to move it down or to move it up. You don't need any force to say you want to stop it. So now, to move it down now, you will need to increase this force to be enough to be equal to mu n. So, to move body down now, you will need additional force P here. So P will be equal to mu n minus mg sine theta. And you can also say n tan phi minus n tan theta. Very straightforward, simple like that. And if I now want to move the body up, frictional force will act down. And P. So this P must overcome the limiting frictional force and the components of this weight mg sine theta downward. So to move body up, P will now be equal to mu n plus mg sine theta, which is equal to n tan phi plus n tan theta. So that's why you'll be asked, what is the range of force? What is the range of frictional force? What is the range of force that is necessary to move the body, to hold the body, to cause motion? So you might need force to move it down, and you might need force to move it up. So that's the conditions that you can experience. Those are the conditions that you can experience for body on inclined plane. Now let's talk about self-locking. If a state of impending motion in a body or mechanism cannot be brought about by an applied force, however light the force may be, then the body or mechanism is said to be jammed or self-locked. The condition is frequently associated with a force in a particular direction, and the reversal will release the body. So what are we talking about? At a point, if the force is acting like this, because we said in a particular direction, so you might face this kind of situation. Maybe when you are trying to push a body up an inclined plane and you are applying straight force, at the point it will be like it has met a wall. So no matter what you do, the body will not move. So for different systems, different situations, we come across this self-locking, and we are trying to devise a way to calculate what angle will that take place for the force in a specified direction. Now we have this, and we are trying to see a situation where the force P, no matter how large, infinite the size may be, it will move the body. Let's look at what that will be. If this force is trying to move this body up, we are going to have F downward. We are going to have F downward, and N will be upward. So then we will now say this one will be W cos theta, and this one we have W sine theta. Now, as we have it here, there is a relationship between this one and this one, and which is the same thing as relationship between this one and this one. So let's look at it. Along the plane and perpendicular to the plane, we have something like this. We have N W cos N cos theta. We have W sine theta. Looking at this, we are now trying to see a situation where the relationship between this one and this one will be so large that no matter how this force here will be, it will not move this body. Now we have this, we have this. Yes, let's see. we might have, since it's moving the body upward, we will have F here, and that is N tan theta. We have phi rather is angle of friction. Angle of friction. Now, looking at this, we can now see that N will be equal to W cos theta. We have it like this. This is P, and this is theta. Yeah. So we are going to have plus P sin theta. We can also see that P cos theta is equal to N tan theta plus W sin theta. Now, let me bring this here. Oh, N tan phi. Yes, N tan phi plus W sin theta. Now, I want to bring this one to this place. So, P cos theta is equal to tan phi into W cos theta plus P sin theta plus W sin theta. Looking at this, we can divide through by cos theta, isn't it? We can. So let's cut. We have tan theta. We have tan theta. So P equals tan phi into W plus P tan theta plus W tan theta. Again, let us bring this one here and we expand. So we have P into 1 minus tan theta tan phi is equal to W into tan theta plus tan phi. Looking at this, we can now see our P will be equal to W into tan theta plus tan tan phi. Tan theta plus tan phi. Okay, let me write it again. We can now bring this one here. So we have P into 1 minus tan theta tan phi is equal to W into tan theta plus tan phi. So P is equal to W into tan theta plus tan phi over 1 minus tan theta tan phi. And you know from our identity, tan theta plus tan phi over 1 minus tan theta tan phi is sum of the tangent of the sum of the two angles. So we are going to have W into tan theta plus phi. And we will have infinite figure when tan theta plus phi is equal to 90. So tan 90 degrees is equal to infinity. And therefore, tan theta plus phi, theta plus phi will be equal to 90. So for self-locking in this situation, theta will be equal to 90 minus phi. That is the angle of friction. That is the angle of friction. That is the angle of friction. So we can also look at it just from the diagram alone. I just try to prove it to you that for ease and ease. Another way you can look at it is this is W. You have P like this. And we have N F like this. N like this. This one is theta, you know. And this place too is theta here. And since they are at right angles to each other, our r will just be square root of n squared plus f squared. You know that. And we know the relationship between them. So it has afforded us to know the angle between the n and the f. And that angle is theta. Is phi. That angle is phi. Since f over n is equal to this. And so which is half tan. So that is the angle. That's the angle. So if we now have it like this, we can now say our situation is like this. P W R. What is this one? The total angle between the resultant and the vertical is equal to theta plus phi. You can see. So either by triangle, either by resolution of vector, either by Lami's theorem, we can get it easily. But let's just resolve. We can see from this place that P is equal to R sine theta plus phi. Because we have gotten it here. We can see that our W, and our W is equal to R cos theta plus phi. So P over W is equal to tan theta plus phi. Or we can say P equals to W tan theta plus phi. For infinity, theta plus phi must be equal to 90 degrees. Therefore, theta will be equal to 90 minus phi. So for self-working or jamming, in this situation, theta will be equal to 90 minus phi. Now let's work some other examples.